Welcome to The Explainer. Today, we're diving into the hidden chemical war that's happening all around us and even inside us. It's this incredible battle between opposites that decides everything from the sour tang of your lemonade to whether your heartburn medicine actually works. Yep, we're talking about acids, bases, and salts.
You know, it all kicks off with something super simple, something you've noticed in your own kitchen. Some things, like lemons, are just intensely sour, and other things, like soap, well, they're bitter and feel kind of slippery. And believe it or not, these basic properties, they're the first clues in a really powerful chemical story.
Okay, here's our game plan. First, we're going to meet our two main players, acids and bases. Then, we'll zoom way in, down to the molecular level to see what really makes them tick. After that, we'll explore what happens when these opposites attract, see how that single reaction shapes our daily lives, and finally, uncover the surprisingly huge world of what they create together.
All right, first up, let's meet our two main characters, acids and bases. Now, at their absolute core, they are chemical opposites. And it's their constant interaction that runs countless processes happening all around us, and yeah, even inside of us.
So on one side, you've got your acids. They're the reason citrus fruits have that sharp, mouth-puckering sour taste. And on the other side, we have bases, sometimes called alkalis. They're usually found in things like cleaning products and have that characteristic bitter taste and, that really distinct slippery, soapy feel.
So how do we tell them apart without tasting them? Well, this is where it gets cool. A super simple litmus test gives us a color-coded answer. Acids turn blue litmus paper red, bases turn red litmus blue. Easy, right? And then there's the pH scale, which is basically a ruler for acidity. Anything below a 7 is an acid, and anything above 7 is a base. But, taste and feel, that's just the surface level stuff. What's actually going on with the molecules to make something an acid? Well, our understanding of this has changed a lot over time, so let's check out a few key theories that really cracked the code. So the first big idea came from a guy named Svante Arrhenius. He suggested that if you dissolve something in water and it lets go of hydrogen ions, that's H+, then it's an acid. If it releases hydroxide ions, OH-, it's a base. It was a fantastic start, but it had one major blind spot. It only worked for reactions happening in water.
Right, so to explain what happens outside of water, the Bronsted-Lowry theory came along and basically changed the game. It simplified everything. It said an acid is just a proton donor, and a base is a proton acceptor. It's like a chemical game of catch, and it can happen almost anywhere, which just blew the whole definition wide open.
And then, finally, the Lewis theory zoomed out even further, giving us the biggest, broadest definition of them all. This one doesn't even focus on protons. It's all about pairs of electrons. A Lewis acid accepts an electron pair, and a Lewis base donates one. This is like the master key that unlocks our understanding of reactions that don't even involve hydrogen.
So here's the thing. It's not that one theory was wrong and the next one was right. They're more like different lenses, each one built on the last to give us a sharper, more complete picture of how these fundamental chemical opposites really work in all sorts of different situations.
Okay, so now that we know what they are, what happens when we actually mix them together? This is where their whole opposite nature leads to one of the most important reactions in all of chemistry, neutralization.
And this shows the process perfectly. When an acid like hydrochloric acid meets a base like sodium hydroxide, they react. The H+ from the acid and the OH- from the base get together and form neutral water. And the other parts, the sodium and the chloride, they combine to form a salt, in this case sodium chloride, which you probably know is regular table salt.
Now, this isn't just a quiet little mixing of liquids. Oh no, it's a powerful exothermic reaction. When a strong acid and a strong base neutralize each other, they release a surprisingly consistent amount of energy as heat. That number you see, that's just how much power is unleashed when these two opposites finally find their balance.
And this power of neutralization isn't just something for a lab. It is constantly at work all around us. And this is why it really matters. It's a core principle we use to solve real-world problems every single day.
For instance, if you've ever had that awful feeling of heartburn, you're feeling the effects of too much stomach acid. So you take an antacid tablet, which has a weak base in it, like magnesium hydroxide. You are literally performing a neutralization reaction right there in your stomach to make yourself feel better.
And we use this same exact principle on a massive scale. Farmers treat acidic soil with a base like lime to create the neutral conditions that most crops need to grow. And wastewater treatment plants are carefully neutralizing water to make sure it's safe before it goes back into our rivers and lakes.
So every single time an acid and a base cancel each other out, they leave something important behind. We've talked about the water, but let's focus on that other product, a salt.
In chemistry, the word salt means way, way more than just the stuff you sprinkle on your fries. It's the general name for any ionic compound that's formed from one of these neutralization reactions. It's what's left behind after the acid and base have done their thing.
And these salts are incredibly diverse, and they are absolutely essential to our modern world. I mean, from the Epsom salt that soothes sore muscles and the fertilizers that grow our food, to the industrial production of glass and the rock salt that keeps our roads safe in winter, we totally rely on them.
So, the big takeaway here is this. From our own bodies to the health of our planet's soil and water, this delicate chemical balance is everything. In this world of chemical opposites, it's equilibrium that allows life to thrive. And that leaves us with a final, really critical question to think about. What happens when we push that balance too far?